I welcome you all to the new session of Fourier integral transforms. In this session, we shall be discussing about the convolution theorem on the Fourier transforms as well as the Parsevals identity for the Fourier transform or the Parsevals identity for the sine and cosine transforms. So let us start the lecture with the convolution theorem. So as we know that the convolution means that the two functions are being multiplied. So the multiplication of the two functions or the convolution of the two functions where the functions are defined by f of x and g of x. So if we take the multiplication of fx and gx, so their multiplication or the convolution is defined by a function which is represented as 1 by root 2 pi integral. The limits are from minus infinity to infinity f of u into g of x minus u into du. So this is the convolution of the two functions f of x and g of x. So when we apply the convolution theorem on the Fourier transform means that when the Fourier transform is applied on the multiplication of the two functions f of x and g of x, that is if f of fx into gx is applied, which can be found to have the form of that the convolution theorem states that the f of fx into gx is nothing but the individual Fourier transforms on the functions. So it is the multiplication of the Fourier transforms of the individual function, that is it is equal to f time f of fx into f of gx, which is equal to f of fx can be written as f of s and f of gx can be written as g of s. So what we find that when f of fx into gx is carried, then it is nothing but the individual multiplication of the Fourier transforms on the individual function, that is fs into gs. So this is the convolution theorem on the Fourier transform. So let us see the proof of the convolution theorem. So we have already defined that the convolution of the two functions is defined by the equation that f of x into gx is equal to 1 by root 2 pi integral minus infinity to infinity fu into g of x minus of u into du. So now what shall we do? We shall take the Fourier transform on both sides of the above equation. So when we apply the Fourier transform on both the sides, we get this type of equation. So now solving the right hand side of the equation, we are taking the Fourier inside, or we are applying the definition of the Fourier transform. So when we apply the equation, the definition of the Fourier transform, this whole function is treated as the f of x. So we treat this whole equation as f of x, and we know that the definition of the Fourier transform is nothing but 1 by root 2 pi integral minus infinity to infinity. This part is our f of x, which is to be multiplied with the kernel e to the power iota sx into the integration is carried over the variable x. So this is our Fourier transforms definition, which is 1 by root 2 pi integral minus infinity to infinity fx e to the power iota sx into dx. So we get this equation on applying the Fourier transform. So now since we have to apply the integral over dx, so we have taken the quantities which are integrable over the x variable. So what we get this integral, which is minus infinity to infinity g of x minus u e to the power iota sx into dx, because we are having this term of f of u, but first of all we are applying the integration over the x variable. So we have taken this f of u out of the first integral. So what we get this equation, and we know that this 1 by root 2 pi integral infinity to infinity g of x minus u e to the power iota dx has to be solved first. So when we solve it, we have used the properties of the Fourier transforms. So we apply the shifting property, so we can write it as e to the power iota us into g of s. So For this, we have written it as Fourier of g of x minus of u. On this, we have applied the shifting property. So upon application of the shifting property, we come at e to the power iota us into gs, because the a quantity was the u factor. So u was our a factor. So we have in our exponential e to the power iota us into gs. So now this g of s is taken out of the integration, and the integration is carried over this quantity. So what we find is, that this is nothing but the definition of the Fourier transform. So for this integral, we can write it as this is your f of s. So we were already having g of s. So g of s into f of s gets multiplied as the resultant of the right hand side of the equation. So what we find here that our Fourier transform of f of x into gx is nothing but the multiplication of the individual Fourier transforms on the functions. So we have this, that f of fx into gx is equal to f of fx into f of gx, which is equal to f of s into g of s. We can also derive the convolution theorem for the inverse transformations. So when we take this Fourier to the right hand side, what is left behind is the f of x into g of x. So we have here that f inverse of fs into gs is equal to f of x into g of x, where this f of x can be written as the inverse Fourier transform. So it can be written as f inverse of f of s, and gx can be written as f inverse of g of s. So this is the convolution theorem, and I hope that you have understood the proof and the statement of the convolution theorem. So let us now look at the Parseval identity for the Fourier transform. So the statement of the Parseval identity is that if we have f of s and g of s, where f of s is the Fourier transform of f of x and g of s is the Fourier transform of g of x, then what we have that if the integration is carried over the f of s into g bar s, where this g bar s is the complex conjugate of the gs function, then this integral will be equal to minus infinity to infinity fx into g bar x into dx, where the g bar x is the complex conjugate of the gx function. Similarly, the second part of the Parseval identity proves that it is minus infinity to infinity modulus of fs square ds is equal to minus infinity to infinity modulus fx square into dx. So this is the statement of the Parseval's identity. So let us look at the proof of the first and the second part of the Parseval's identity. So as we can see the statement, that the first part is that integral minus infinity to infinity fs g bar s ds is equal to minus infinity to infinity fx g bar x into dx. So we start with the right hand side of the equation. So the right hand side of the equation is minus infinity to infinity fx g bar x dx. So this g bar x, fx and g bar x are also known as the inverse Fourier transforms. So we apply the inverse Fourier transform on the g bar of x. So using the definition of the inverse Fourier transform, we can write this g bar x as 1 by root 2 pi integral minus infinity to infinity g bar s e to the power iota sx into ds. Now, what has happened? Because gx, if we have taken gx, then gx is nothing but it is 1 by root 2 pi gs e to the power minus iota sx. But upon taking the conjugate of the function, so gx will be replaced by g bar x, gs will be replaced by g bar s, and this e to the power minus iota sx on conjugation will become e to the power plus iota sx. So making these substitutions for the g bar x, we get the equation that it is 1 by root 2 pi minus infinity to infinity g bar s into e to the power iota sx into ds into dx. So we have now the equation as minus infinity to infinity fx g bar x into dx is equal to 1 by root of 2 pi integral minus infinity to infinity g bar s into ds. And since the integral is to be carried over the x variable now, so we club the e power iota sx with f of x to have the equation as minus infinity to infinity fx e power iota sx into dx. This is just a rearrangement of the term, and we club this 1 by root of 2 pi with the second integral, and this second integral is nothing but the basic definition of the Fourier transform, which is the fs. So this we have the equation that it is equal to minus infinity to infinity g bar s into f of s into ds. So we have proved the first part of the Parsevals identity, that integral minus infinity to infinity fx g bar x dx is equal to integral minus infinity to infinity g bar s fs into ds. To looking at the second part of the Parsevals identity, we don't find any gs or g of x or conjugates of the functions. So it means that since there is a square of the functions involved in the statement of the Parsevals identity, so we have to equate that our fs is equal to gs, or our fx, the function fx, is equal to g of x. So let us take that our function f of x is equal to g of x. If our functions are equal, then definitely our Fourier transforms will also be equal. Therefore, g of s will be equal to f of s, and similarly their conjugates will also be equal to each other. Therefore, g bar s will be equal to f bar of s. So now, putting all these substitutions in the first part of the equations, what we get here for the g bar x, we have written it as f bar x, and for the g bar s here, we have written it as f bar s. So the equation takes the shape that it is now of the fashion that it is minus infinity to infinity fx into f bar x dx, which is equal to minus infinity to infinity fs into f bar s into ds. So we know by this theorem that if any function is there, so we can write that x into modulate of, so we can write that x into conjugate of x is equal to the modulus of the x square. So using the property of the complex numbers, we can write this as fx into f bar x is nothing but f of x bar modulus square, and this f of s into f bar s is nothing but fs modulus square. So we have derived our second part of the Parsevals identity. So this is the proof of the Parsevals identity. So I hope that you have understood the Parsevals identity is further applied on the cosine transform and the sine transform. So it takes the equation as it is 2 by pi integral 0 to infinity Fourier cosine transform of the function f of x into Fourier cosine transform on the function gx into ds, which is equal to 0 to infinity on the multiplication of the function itself, that is fx into gx into d of x. And the second equation can be represented as it is 2 by pi integral 0 to infinity modulus of Fourier cosine transform square into ds will be equal to 0 to infinity modulus of the function square into ds. Similarly, for the sine transform, the equations can be represented as 2 by pi 0 to infinity integral Fourier sine transform for the function f of x into Fourier cosine transform. Fourier sine transform of the function g of x into ds will be equal to the integral 0 to infinity of the functions fx into gx dx. Similarly, the second part of the Parseval identity for the Fourier sine transform will be written as 2 by pi integral 0 to infinity modulus of Fourier sine transform on the function square into ds will be equal to 0 to infinity modulus of the function itself squared into dx, that is modulus of fx bar square in dx. So this is the Parseval identity for the Fourier sine transform and the Fourier cosine transform. So now we shall apply these Parseval's identity for the application of the numericals, and let's see how we shall be able to solve the integrals. So before solving the numericals related to the Parsevals identity, this is an extract of the formulas from the book H.K. Das, where it has mentioned some of the functions and their Fourier sine transform and Fourier cosine transforms. So this has been shown because before solving the Parsevals identity, we should be well aware of the formulas that if we have a certain function, what will be the Fourier sine transform or what will be its Fourier cosine transform. So having an idea of the function and its Fourier sine and cosine transform, it is very easy for us to solve the Parsevals identity, because then by looking at the equations that the numerical we have to solve, if we can judge what is the function and what will be the result or what, then we can immediately judge that which Parseval identity we want to apply. The Parseval identity is to be applied for the individual transforms, or it has to be applied for the Fourier sine or the cosine transform. So we have the equation such as that if the function is 1 when the x is lying between 0 to b, or it is 0 when x is greater than b, then the Fourier sine transform is having the formula of 1 minus cos ps by s. And for the same function, the Fourier cosine transform is sine of ps by s. If we have x upon x square plus b square, then the Fourier sine transform is pi by 2 into e to the power minus bx. And if the function is 1 upon x square plus b square, then the Fourier cosine transform is pi by 2b e to the power minus bx. So we should be able to judge that which function or which transforms we should choose to get a desired result. Similarly, if you look at the function e to the power minus bx, the Fourier sine transform is s upon s square plus b square, and for e to the power minus bx, the Fourier cosine transform is b upon s square plus bx. So I would recommend that to learn some of the functions and their results for the Fourier sine and cosine transforms, so that you are able to apply the Parsevals identity on the numericals. So let's look at the numerical related to the Parsevals identity. So the first problem is that we have to evaluate the integral from 0 to infinity 1 minus cos x by x square dx. So now what we see here the function as 1 minus cos x by x. So as I have told you, I have showed you some formulas related to the Fourier sine transform and the Fourier cosine transform. So we shall be able to judge that which transform we should apply to have a solution for the integral. So as we know that if we choose a function that f of x is 1 when x is lying between 0 to b, or it is 0 when x is greater than b, then the Fourier sine transform on such a function is having the result of 1 minus of cos bs upon s. So this 1 minus of cos x by x is similar to the Fourier sine transform result of the function, which is 1 minus of cos bs by s. So upon judging this type of functions and its Fourier transforms, we are able to apply the Parsevals identity for the sine transform. So when we have judged our function and its Fourier sine transform, and we can relate that Fourier sine transform to the something function to the question itself, then we are able to think that which Parsevals identity we should apply. So since this is a Fourier sine transform function, so we shall apply the Parsevals identity for the sine transform. So the Parsevals identity for the sine transform was 2 by pi integral 0 to infinity Fourier sine transform on the f of x function into Fourier sine transform on the gx function into ds is equal to 0 to infinity fx into gx dx. So now we substitute the results, and we here, because we have a square formula here, so we choose that our functions f of x and g of x both are equal. So we have this as 2 by pi integral 0 to infinity 1 minus of cos ps by s into 1 minus of cos ps by s into d of s is 0 to b, because the function here is defined for x lying between 0 to b. And instead of 0 to infinity, now the results are from 0 to b, because after b greater than b values, the function is assuming to be 0 value. So our f of x is taking the value 1, g of x is also taking the value 1. So now what we are here with. So now since this 1 minus of cos x term is there and there is no b involved, the b value is taking the value of 1 here. So we make a substitution that let b is equal to 1, and we get the equation as 2 by pi 0 to infinity 1 minus cos s by s square ds, and upon integration of the right hand side we get this as x, and the limits are from 0 to 1 because we have assumed that our b value is 1. So the right hand side takes the value of 1, and further going to the further substitutions, also the s is replaced by x variable. So we make a substitution that let s is equal to x, so that integral 0 to infinity 1 minus cos x by x square dx is equal to pi by 2. This 2 by pi is taken to the right hand side, so it becomes equal to pi by 2. So see how easily by using the Parsevals identity we were able to calculate this important integral. So in this Parsevals identity results, we should be able to judge the function for which we shall get a particular formula or the Fourier sine transform, cosine transform, and that Fourier sine cosine transform is the question itself. So let us again see another problem related to the Parsevals identity. So let us consider this equation that we have to solve the integral 0 to infinity sine at by t into a square plus t square dt is equal to pi by 2 into 1 minus of e to the power minus a square by a square. So again we have to judge which identity, which transform we have to choose. So we know that if we choose a function g of x which is e to the power minus bx, so we get the Fourier cosine transform for such a function to be b upon s square plus b square. So there is a term related to some 1 upon a square plus t square which is of the form of this b upon s square plus b square, because there is a constant term involved here. So there is no t in the denominator. So we have chosen this g Fourier cosine transform of e to the power minus bx to be b upon s square plus b square. So the remaining function which is left is that this is sine at by t. So we have to think a Fourier sine transform or cosine transform which is having the form of sine of s upon s. So if we choose the function as f of x is 1, 0 for x lying between 0 to b, and it is 0 for x greater than b, then the Fourier cosine transform of that function is sine of bs upon s. So this sine of bs upon s is related to the sine of at by t, and 1 upon a square plus t square is related to the cosine transform of the function e to the power minus of bx. So we will now apply the Parsevals identity for the cosine transform. So the Parseval identity for the cosine transform has the statement that it is 2 by pi integral 0 to infinity Fourier cosine transform of the function into the Fourier cosine transform of the gx function into ds will be equal to the 0 to infinity fx into gx into dx. So now we substitute the values of the Fourier transforms and the functions. So what we get here is 2 by pi. For f of c, we get the result as sine of bs by s. For gc of s, we get the result as b of s square plus b square into ds. For the function here, it is 1 and it is e to the power minus bx. And the results are that it is 0 to a, because we will be substituting that b is equal to a. So initially you can also write here as b, because the limits of x was lying between 0 to b. So we make a substitution that in the final result, we are not having any s, we are having t's. So we replace our s by t and we substitute the b equal to a. So we get the result that it is 2 by pi integral 0 to infinity sine at by t into a upon a square plus t square into t square into dt will be equal to e to the power minus ax upon minus of a, because we have replaced b by a and the limits are also from 0 to a. So when we do the integration and we substitute the limits, we get the result as e to the power minus a square minus e to the power minus 0 upon minus a, and e to the power 0 is nothing but 1. So it is 1 minus of e to the power minus a square by a, and there is an a in the denominator outside the bracket also. So we have here that we get the result that 0 to infinity sine at by t into a square dt is equal to, we have shifted this 2 by pi to the right hand side. So we get this is as pi by 2 1 minus e to power minus a square by a square, which is the desired result. So we have solved our question using the Parsevals identity. So basically this just involves your judgment power, that which function you should choose that it is matching the result that is asked in the question. So meet you again, and thank you.